A jet engine swallows 1,000 pounds of air a second. A hangar door weighs 20 tons. In the world of aviation logistics, physics is the only judge. We are documenting 6 deaths inside airports where the safe routine became a death trap. This is a forensic analysis of tragedy, not entertainment. If you value your life, never bet against the laws of motion. It is a bet you will always lose. The tarmac of El Paso International Airport was slick with winter rain on the morning of January 16, 2006. A Monday that began with the heavy industrial rhythm of global travel. The air was cold, smelling of damp concrete and unburnt kerosene, a sensory baseline familiar to anyone who works the ramp. Continental Airlines Flight 15-15, a Boeing 737-500, sat parked at Gate B10, a massive assembly of aluminum and titanium scheduled for a routine departure to Houston. However, the machine had developed a minor imperfection, a suspected oil leak in the number 2 engine on the right wing. In the high-stakes world of aviation, even a single drop of fluid in the wrong place grounds a 50-ton aircraft, demanding immediate human intervention. This is where Donald Gene Holberg entered the narrative. At 63 years old, Holberg was a veteran contract mechanic, a man whose hands knew the cold texture of fuselage metal better than they knew his own pockets. He was not a reckless novice. He was a seasoned professional who understood that the airport is a hostile environment disguised as a workplace. Yet the greatest threat to an expert is not ignorance, but comfort. When you work next to monsters every day, you eventually stop fearing their teeth. The task required a specific diagnostic procedure known as a leak check. To find the source of the dripping oil, the engine had to be running. The static pressure of a parked plane often hides leaks that only appear under the intense stress of operation. The plan was simple but inherently dangerous. The pilots in the cockpit would run the right engine at elevated power settings, while Holberg stood on the tarmac below, watching the casing to pinpoint the seep. He was tethered to the aircraft by a headset wire, his only link to the men controlling the throttle. The Boeing 737-500 is powered by 2 CFM56 turbofan engines, engineering marvels designed to inhale massive quantities of air to generate thrust. At idle, the front fan blades spin with a deceptive laziness, creating a gentle breeze that feels harmless. But the moment the throttle advances, the physics of the environment change radically. The engine transforms into a localized vacuum singularity. Aviation safety protocols define a strict ingestion zone, an invisible semicircle extending from the engine inlet where the suction is strong enough to pull a human being off their feet. The danger of this zone is its invisibility. Air does not change color when it accelerates to lethal speeds. At approximately 9:01 a.m., the pilots received clearance to increase the engine power to 70% of its maximum rotational speed. This is not a test setting. This is takeoff power. Inside the engine, the titanium blades began to slice the air at thousands of revolutions per minute. The sound on the tarmac shifted from a high-pitched whine to a ground-shaking roar that vibrated in the chest of every ground handler nearby. The rain on the pavement began to dance, pushed and pulled by the violent displacement of air. Holberg focused intently on his job, stepped closer to the cowling. He was looking for a leak, his mind occupied by the mechanical puzzle, momentarily filtering out the screaming threat just feet away. He needed to see the oil. To see it, he had to be close. He stepped past the invisible safety line. At 70% power, a CFM56 engine ingests approximately 2,500 pounds of air every second. This creates a massive pressure differential, a phenomenon known as delta P. The air pressure directly in front of the inlet drops instantly, while the atmospheric pressure behind the object remains constant. This creates a violent, unidirectional force that acts faster than human reflexes. It functions like a horizontal tornado. The engine does not distinguish between oxygen molecules, raindrops, or biological matter. It simply feeds. The transition from a routine maintenance check to a catastrophic event took less than a second. As the engine reached its target RPM, the suction force overcame the friction of Holberg's boots on the wet, rain-slicked pavement. There was no time to scream, no time to signal the cockpit, and no time to regret the step. At that range, the force pulling him in was absolute and unstoppable. Donald Holberg was lifted from his feet and pulled directly into the spinning titanium fan blades. The clinical reality of this interaction is absolute. The impact with the fan assembly, rotating at such extreme velocity, resulted in instantaneous, fatal trauma. The biological structure of the subject was simply incompatible with the mechanical rigidity of the fan blades. There was no suffering, only an immediate loss of life. The machine, detecting a massive foreign object imbalance, shuddered violently. On May 22, 2001, the Texas sun was already baking the ground, creating a stifling, blinding environment for the thousands of ground workers who keep the global aviation network breathing. In this chaotic ecosystem, the ramp agent serves as the nervous system, guiding blind giants through a maze of obstacles where a single misstep can result in catastrophe. Michael Rennie, a 36-year-old ground coordinator, was part of this critical infrastructure, a man whose daily routine involved walking inches away from rolling machinery that weighed as much as a locomotive. He was not a pilot, but his role was just as vital. On the ground, the pilots are essentially visually impaired, unable to see the extremities of their own machine. They rely entirely on the eyes and signals of men like Rennie to navigate the crowded ramp without crushing metal or bone. The aircraft in question was an American Airlines McDonnell Douglas MD-80, a sleek, twin-engine workhorse of the domestic fleet, known for its long, slender fuselage and rear-mounted engines. To a passenger looking out the window, the Mad Dog, as it is affectionately known, seems agile, but on the ground, it is a clumsy beast with a wingspan of nearly 108 feet. The physics of moving such a vessel are deceptive, specifically regarding the pivot point. When an aircraft turns on the ground, it rotates around its main landing gear, which acts as a fulcrum. This creates a geometric lethality known as the sweep. While the nose of the plane might move only a few feet during a turn, the wingtip, located far from the center of rotation, traces a massive accelerating arc. The further out you are from the pivot, the faster the metal moves. This is simple geometry, but on the noisy ramp, geometry can kill. Flight 1628 was preparing for departure, its engines whining with the high-pitched frequency of the auxiliary power unit. The pushback tug, a powerful squat vehicle designed to move mountains, had successfully shoved the 80-ton aircraft away from the gate. The tow bar was disconnected, the bypass pin removed, and the tug driver waved off. The pilots were now in control, ready to taxi to the runway. Rennie's job was to act as the wing walker, ensuring the path was clear of other vehicles or debris. He was the human sensor in a blind spot. The pilots, sitting high in the cockpit, physically cannot see their own wingtips. The swept-back design of the MD-80 completely hides the danger zone from their view. As the engines spooled up to taxi power, the aircraft began to move forward and initiate a sharp turn to align with the taxiway. This was the moment the trap was sprung. The calculation of space is a constant mental process for ground crews, but human depth perception is fallible, especially against a backdrop of moving vehicles and shimmering heat waves. Rennie was standing on the tarmac, confident in his position relative to the aircraft. He believed he was outside the arc of the wing. He was wrong. As the pilot applied the rudder to swing the nose, the physics of the lever arm took over. The right wing of the MD-80 began to sweep backward and outward, accelerating through its arc much faster than the fuselage itself. To the pilots, the movement felt slow and controlled. To Rennie, the silver leading edge of the wing became a rapidly approaching wall of aluminum. The final moment stretched out. He likely saw the approaching metal a split second too late to escape. The wing of an airplane is designed to slice through the atmosphere at 500 miles per hour. It is a hardened aerodynamic blade, reinforced with ribs and spars. When it struck Michael Rennie, the interaction was purely kinetic. The leading edge of the wing impacted his head with the force of a battering ram, transferring the momentum of an 80-ton object into a biological form in less than a blink of an eye. The clinical outcome of such a collision is non-negotiable. The structural integrity of the human cranium cannot withstand the sheer mass and momentum of a turning airliner, even at low taxi speeds. The mechanics of consequence resulted in immediate, catastrophic, blunt force trauma. There was no prolonged struggle, no medical intervention that could reverse the physics of the impact. The energy transfer caused instantaneous loss of consciousness and fatal injury before his body even hit the pavement. The pilots, insulated in their cockpit and separated by 100 feet of aluminum, felt nothing. They continued the taxi, unaware that their machine had just caused a fatal accident, until the frantic signals from other ground personnel forced them to halt. The residual echo of the scene was a stark contrast between the massive, indifferent machine and the fragile human form lying still on the concrete. The MD-80 sat idling, its engines whining with potential energy, while the silence of the tragedy spread outward from the impact zone. An investigation would later analyze the communication protocols and the positioning of the wingwalker, but the fundamental cause was the brutal, unforgiving geometry of the ramp. It serves as a grim reminder that in the presence of heavy machinery, a miscalculation of inches is a death sentence, and the blind spots of a giant are always larger than the safety of a man. March 14, 2007 brought a violent shift to the usually scorched atmosphere of Sharjah International Airport in the United Arab Emirates. While the region is known for its blistering heat and stillness, the spring transition often triggers sudden, ferocious squalls that turn the open desert into a wind tunnel. On this Wednesday, the sky turned a bruised purple and the air pressure plummeted, signaling the arrival of a severe storm front that would test the structural limits of the airfield. In the shadow of the control tower, the maintenance hangars stood like fortress walls, massive enclosures designed to house commercial airliners. These are not simple garages. They are industrial cathedrals of steel and corrugated metal, built on a scale that dwarfs the humans who maintain them. The most critical component of a hangar is its door system. These are not hinged barriers, but gigantic, sliding slabs of steel, often standing 40 feet tall and weighing dozens of tons. They run on precision ground rails, moving on steel wheels that reduce friction to a minimum so that electric motors can slide them open. However, this engineering efficiency creates a deadly vulnerability known as the sail effect. A hangar door presents a surface area of thousands of square feet. When the wind blows against a flat wall, it exerts pressure. When that wall is mounted on wheels, that pressure translates into kinetic energy. Saif bin al-Sheikh, a dedicated member of the ground support team, was on shift as the winds began to howl across the apron, gusting with a velocity that rattled the teeth of the facility. The noise inside a hangar during a storm is deafening, a constant, booming echo of metal flexing against nature. Saif noticed a critical issue with one of the massive sliding doors. The locking mechanism, a steel pin designed to anchor the structure to the ground and prevent movement, was struggling against the lateral force of the gale. To a diligent worker, a rattling door is a problem to be solved, a mechanical fault that threatens the expensive aircraft inside. He made the decision to intervene, a choice driven by the instinct to protect the facility, but blinded by the scale of the forces at play. He approached the gap between the sliding door and the stationary structural column of the hangar frame, intending to manually adjust the roller or secure the latch. He was operating under the illusion that the door was a static object, a wall that would stay put because it was heavy. But in physics, mass does not equal immobility. As Saif stepped into the narrow recoil zone, the storm outside intensified. A massive, concentrated gust of wind slammed into the exterior face of the door. The physics of this moment are terrifyingly simple. Air pressure multiplied by surface area equals force. With thousands of square feet of metal catching the wind, the door generated tons of lateral thrust, instantly overcoming the friction of the rollers and the resistance of the brakes. The massive steel slab, which usually required a high-voltage motor to budge, was suddenly shoved by the invisible hand of the atmosphere. It broke free. The movement was not necessarily a high-speed blur. It was a lurch of unstoppable momentum. When 20 tons of steel begins to move, it possesses infinite inertia relative to a human body. It does not stop for soft biological matter. Saif was positioned in the pinch point, a fragile vertical line in a world of horizontal force. The realization was brutally fast. The groan of the metal wheels on the track likely gave him a fraction of a second to realize the trap had sprung, but the geometry of the space offered no escape. The closing sequence was a clinical lesson in mass versus biology. The leading edge of the hangar door, driven by the relentless pressure of the storm, impacted his body against the solid steel I-beam of the building's support frame. The medical reality of this compression is absolute and non-negotiable. The structural integrity of the human thorax is designed to withstand gravity, not the crushing lateral force of a moving architectural element. The mechanics of consequence resulted in immediate, catastrophic traumatic asphyxia and multiple fatal injuries. The door did not bounce off. It simply pressed forward until the resistance of the steel frame stopped it, pinning the subject with overwhelming force. There was no prolonged suffering. The pressure was too great, the shock to the system too total to allow for the processing of pain. The storm continued to rage outside, the wind howling through the gaps in the metal cladding, completely indifferent to the tragedy it had just orchestrated inside. When the emergency crews finally arrived, they found a scene of mechanical finality. The door stood rigid, a wall of silence, hiding the result of its brief, wind-driven rebellion. The investigation would later highlight the extreme dangers of operating large surface area doors during high wind warnings, noting that the sheer surface area of the structure turned it into a weapon the moment the wind speed exceeded the friction coefficient of the wheels. But the fundamental cause was elemental. A man tried to impose order on a machine during a moment of chaos, and the laws of physics, amplified by the storm, simply erased him. It serves as a grim reminder that in the environment of an airport, even the walls can become killers if the wind blows hard enough. June 12, 2007, began as a standard Tuesday at Stockholm Arlanda Airport, a hub of Nordic efficiency where thousands of passengers move through sleek terminals every hour, unaware of the industrial underworld beneath their feet. While the travelers walked on polished floors and shopped in bright, duty-free stores, a different reality existed just a few meters below them in the baggage handling facility. This subterranean zone is a mechanical labyrinth of high-speed conveyor belts, diverters, and robotic arms, a deafening world that operates in perpetual motion to ensure suitcases reach their flights on time. It is a place of grease, dust, and the relentless clatter of machinery, where the air smells of warm rubber and hydraulic fluid. Lars-Göran Lindgren, a 63-year-old technician with decades of experience, descended into this noisy environment to address a routine issue. He was a veteran of the airport's infrastructure, a man who knew the rhythm of the belts and the hum of the motors better than he knew the sound of his own voice. To a seasoned professional like Lindgren, the baggage system was not a threat. It was just a tool, a complex assembly of metal and sensors that he had fixed 1,000 times before. But familiarity in an industrial setting is a dangerous sedative. It lulls the brain into believing that the machine is predictable or even tame. The issue of the day was a jam in one of the sorting tunnels, a common occurrence in the chaotic flow of global travel, where a single oversized bag can wedge itself against a guardrail and halt the entire line. Lindgren located the problem area, a critical junction where luggage is shoved from one track to another by a powerful mechanical arm known as a pusher. The system in this sector had paused, its sensors detecting the obstruction. The belts were silent, and the heavy steel arm of the pusher was retracted, waiting. The standard safety protocol for clearing such a blockage is absolute. The technician must physically cut the power to the specific section and secure it with a padlock, a rule designed to ensure the machine cannot restart while a human is inside the danger zone. However, on this specific morning, a critical lapse occurred. Whether due to a miscommunication with the control room or a momentary assumption that the local sensor would keep the system paused, the power remained live. Lindgren stepped into the maintenance access area, a narrow claustrophobic space between the conveyor frame and the concrete wall of the tunnel. He reached in to dislodge the stuck suitcase, his body positioned directly in the path of the pusher arm. He was focused entirely on the physical obstruction, wrestling with the heavy bag, completely unaware that he had just stepped into a trap set by his own experience. The central computer, which controls the entire network, was monitoring the situation with cold, binary logic. It did not know a man was inside the tunnel. It only knew that a sensor was blocked. As Lindgren successfully shifted the bag, the sensor cleared. The computer interpreted this signal not as a human intervention, but as a successful resolution of the jam. The logic of the code was simple. If the path is clear, resume operations immediately to make up for lost time. The system did not see a father or a colleague. It saw a green light in a line of code. Without a warning siren, a flashing beacon, or even a second of delay, the pneumatic pressure returned to the diverter arm. The machine cycled instantly. A baggage pusher is designed to move 50-pound suitcases with explosive force. It is a blunt instrument of momentum driven by high-pressure compressed air. When the computer engaged the solenoid, the heavy metal arm swung out with the speed of a striking snake and the force of a battering ram. It did not strike a suitcase. It struck Lars-Göran Lindgren. The speed of the activation was faster than human reaction time. There was no moment to recoil, no time to realize the mistake. The mechanical arm caught him squarely in the chest, driving him backward with tremendous force. But there was nowhere to go. Behind him, just inches away, was a solid steel support beam, a structural pillar of the airport's foundation that was anchored deep into the concrete. The mechanics of the event were brutal and instantaneous. The human body is soft, filled with air and fluid. The machine is hard, driven by industrial hydraulics and unyielding steel. The force of the pusher compressed his torso against the beam with thousands of pounds of pressure, creating an unyielding pressure point. The clinical reality of this crush injury is absolute. The ribs, the sternum, and the internal organs were subjected to a physical load far exceeding their structural limits. The machine did not recoil. It simply held its position, pinning him against the beam with the indifferent force of a hydraulic press. The silence of the tunnel eventually returned, broken only by the distant hum of other belts in the facility. Lindgren was trapped in the dark, alone with the machine that had just executed a valid command. There was no scream that could be heard over the noise of the terminal above. The system, sensing resistance that did not match the profile of a bag, eventually threw another error code, perhaps motor overload or obstruction detected. But for the man in the tunnel, the distinction was irrelevant. When colleagues finally reached the site, guided by the fault signal on their screens, they found a scene of tragic stillness. The machine had done exactly what it was programmed to do: move an object from point A to point B. It had simply failed to distinguish between a piece of luggage and a human life. The investigation would later cite failures in safety protocols and the absence of a verified power cut. But the fundamental horror remains the cold logic of automation. In the eyes of a computer, a human being in the wrong place is not a victim. It is just another error in the sorting algorithm to be cleared. February 22, 2011 was a typically gray and damp day at London Heathrow Airport, a sprawling concrete city operating under the constant pressure of departure schedules and logistical precision. In this world of immense machines and high-stakes operations, the ground support fleet forms a critical, yet often overlooked, part of the ecosystem. These are the fuel tankers, the baggage carts, and the catering trucks, a swarm of specialized vehicles that service the giants of the sky. Abdelmajid El Haik, a 47-year-old catering truck driver, was a veteran of this environment. He was a small but essential gear in the vast, interconnected clockwork of international travel. A man whose job was to ensure that passengers in first class would receive their champagne and canapes on schedule. His vehicle was not a simple delivery van. It was a mobile hydraulic platform, a highly specialized piece of equipment known as a catering high loader. The core of this machine is the scissor lift mechanism, a set of crisscrossing steel arms that raise a heavy cargo box from the truck's chassis to the level of an aircraft's galley door. The entire system is powered by hydraulics, the simple but powerful principle of using pressurized oil to move heavy objects. A pump forces hydraulic fluid through reinforced hoses into large pistons, which then push the scissor arms apart, lifting the platform smoothly and safely. This process had been completed thousands of times a day at Heathrow for decades. It was considered one of the most routine and reliable operations on the ramp. On this Tuesday afternoon, Abdelmajid was servicing an Emirates flight. He skillfully maneuvered his truck into position, the rear of the vehicle facing the aircraft's fuselage. He engaged the power takeoff, and the familiar high-pitched whine of the hydraulic pump filled the air as he began to raise the platform. He was in the driver's cab, a small enclosed space, but his attention was focused outside, looking up and back at the rising platform, ensuring a perfect alignment with the galley door to prevent any damage to the multi-million-dollar aircraft. He was leaning out of the cab's side window, his upper body exposed, to get the best possible view of the docking process. The platform, loaded with heavy food and drink trolleys, had reached nearly its full height, level with the aircraft door, when a hidden weakness in the system triggered a catastrophic failure. Hidden deep within the undercarriage of the truck was a high-pressure hydraulic hose, a simple component made of reinforced rubber and braided steel. Over thousands of cycles of pressurization and depressurization, exposed to engine vibration and temperature fluctuations, this hose had developed a microscopic invisible stress fracture. At that precise moment, under the immense pressure required to hold several tons of weight suspended in the air, the hose ruptured. The sound would have been a sudden, sharp pop, like a gunshot, immediately followed by the hiss of escaping fluid. The pressurized oil that held the platform up was suddenly gone. The physics of the situation were now governed not by hydraulics, but by gravity. With the pressure instantly vanished, the heavy pistons could no longer support the weight. The scissor lift mechanism, no longer being pushed apart, began to collapse under its own load. The massive steel arms folded in on themselves, and the entire platform with its cargo entered a state of freefall. The descent was not slow. It was an uncontrolled, instantaneous collapse that took less than a second. Abdelmajid Al-Haik was still leaning out of his cab, his focus on the plane above, when the world beneath him disappeared. He was positioned directly in the path of the descending scissor mechanism. The clinical reality of the event was inescapable. The heavy steel frame of the lift structure impacted his upper torso, crushing him against the fixed, unyielding steel chassis of the driver's cab. It was a pure demonstration of physics. The human body cannot withstand the focused impact of several tons of collapsing metal. The outcome was catastrophic compressive trauma and traumatic asphyxia, resulting in instantaneous loss of consciousness and fatal injury. There was no time to react, no time to even process the sound of the hose bursting. When the emergency services arrived, they found a scene of brutal mechanical finality. The catering truck's engine was still running, but the massive lift platform was fully retracted, resting silently on the chassis. The neatly stacked food trolleys ready for a flight to Dubai were a stark, ironic artifact of a routine that had been shattered by the failure of a single, humble component. The subsequent investigation would pinpoint the ruptured hose as the sole cause, a tiny point of failure that led to a total and lethal system collapse. It was a grim testament to the fact that in the world of heavy machinery, safety is only as strong as the weakest link in the chain. August 4, 2010. Long after the last wave of passengers had departed from San Francisco International Airport, a different kind of activity began in the facility's hidden veins. Deep in the concrete tunnels that housed the airport's automated airtrain system, the night shift of maintenance crews went to work. This subterranean world is a place of stark contrast to the bright terminals above. The air is cool and still, smelling of ozone and damp concrete, and the only light comes from humming fluorescent strips that cast long, eerie shadows. Siausi Sika, a 30-year-old technician, was on duty in this quiet, isolated environment. His job was to perform scheduled maintenance on the track, a task that required him to be physically present on the guideway, surrounded by the high-voltage rails and complex sensors that make the system run. The airtrain is a marvel of automation, a fleet of driverless electric vehicles that glide silently on rubber tires, managed by a central computer system located miles away. To the passengers, it is a seamless convenience, but to the engineers who maintain it, its autonomy is a known hazard that must be carefully and deliberately caged before any work can begin. The safety protocol for working in the tunnels is absolute and supposedly foolproof. Before a worker enters a section of track, a command is sent to the central computer, flagging that entire block as out of service. This is like putting a digital padlock on that section of the track, an electronic command that is supposed to act as an impenetrable wall, preventing the system from dispatching any train into that zone. For an added layer of safety, the power to the guideway is also supposed to be cut. On this night, Xiaoxi Sika and his team believed these protections were firmly in place. They had followed the checklist, and the system was supposed to be completely inert. He was working with the complete confidence that he was alone in the tunnel. But software is not infallible. It is a complex web of millions of lines of logic, and sometimes a single line of code can contain a ghost, a hidden error that only reveals itself under a specific, rare set of circumstances. While Sika was focused on his task, a latent software glitch in the airtrain's control system triggered an unscheduled and unauthorized command. The central computer, instead of seeing the digital padlock on the track, received a false signal, a phantom request to run a diagnostic cycle on the very section where Sika was working. The computer was supposed to see a red light, but due to a 1 in a million error, it saw a green one. Miles away, a single empty airtrain car, parked silently at a maintenance bay, received a digital instruction to begin moving. Its internal systems powered on, its headlights flickered to life, its doors closed with a soft pneumatic hiss. Then, with no human driver and no warning horn, it began to roll forward, accelerating smoothly and quietly into the darkened tunnel. The air train does not roar like a subway. It moves with an eerie quiet, the soft hum of its electric motors and the gentle whir of its rubber tires on the concrete guideway being the only sounds it makes. In the echoing tunnel, these subtle noises were likely completely masked by the sounds of Sika's own tools. He was focused on his work, his back to the direction of the approaching vehicle, trusting the layers of digital safety that were supposed to be his shield. The first sign of danger would have been the sudden bloom of the train's headlights, cutting through the gloom, painting the tunnel walls in a harsh, advancing white light. But in that narrow, enclosed space, there was nowhere to go. The guideway is flanked by high-voltage rails and concrete walls, creating a narrow trap with no room for a person to stand clear. The time between seeing the bright lights and the moment of impact would have been less than 2 seconds, not nearly enough time for the brain to process the threat and command the body to move. The clinical reality of the event was a simple, brutal equation of mass and momentum. The automated vehicle, weighing several tons and moving at a steady speed, did not have a driver to hit the brakes or a horn to sound a warning. It simply continued to execute its flawed command. The front of the vehicle struck Xiaoxi Sika from behind. The impact was a matter of pure physics. The structural limits of the human body are no match for the kinetic energy of a moving train. The mechanics of the event were absolute, resulting in catastrophic blunt force trauma and non-survivable injuries. The train did not stop. Its sensors, not designed to detect such an impact, registered nothing unusual. It continued its ghostly journey through the maintenance sector, its internal computer unaware that it had just encountered anything more significant than a slight vibration. It eventually glided to a halt at its designated endpoint, its doors sliding open to an empty, silent platform, its mission completed as programmed. The residual echo of the tragedy was the sight of his tools lying abandoned on the track under the harsh work lights. The investigation that followed would take months, untangling the complex digital error that led to the fatal dispatch. The ghost in the machine was eventually found and patched, a few lines of code rewritten to prevent the tragedy from ever happening again. It was a sterile, technical solution to a profoundly human loss, a reminder that in our increasingly automated world, the most dangerous threats are the ones we cannot see, hidden in the silent logic of a computer program. We built these airports to be cathedrals of efficiency, but we turned them into meat grinders for the unwary. Looking at the world your children and grandchildren are entering, where machines make the life and death decisions, would you honestly tell them to take a job on the ramp today? Or is the modern workplace too cold-blooded for a human being to survive a 40-year career? Write your honest advice to the next generation below. If you still believe the worker is worth more than the machine, hit like and subscribe.